Good afternoon. My name is Michele Surico, and I'm going to present the program's project approach to maintenance management. The Research Project Programs, which is the acronym for Prognostic-Based Reliability Analysis for Maintenance Scheduling, was funded by the EU Horizon 2020 Research and Innovation Program, and its consortium includes partners coming from 5 different European countries. Even more in a time of crisis, plant managers aim to contain maintenance costs by a careful management of all production equipment. This aspect has been heavily impacted by the industrial Internet of Things that leverage sensor equipment machine to deliver large amounts of data for real-time decision-making. The predictive maintenance strategy exploits those data to determine when a resource will no longer be fit for purpose, and in doing this allows to lower the cost associated to corrective maintenance activities up to 50%. However, while the addition of specialized sensor has a reduced impact on new equipment, legacy equipment seldom offers a sensitization level high enough to directly exploit such approach. The cost of instrumenting an old but still fit for production piece of equipment includes installation of new sensor, as well as the additional maintenance that they will require. Even when not taking into account these additional costs, a successful predictive maintenance strategy still requires to know how to model the equipment behavior. Alternatively, data-driven methods may be deployed, but they have to face the scarceness of historical data. Once the remaining useful life is known, plant managers still have to determine a maintenance management approach that minimizes the overall maintenance costs, maximizes the system availability, improves the use of equipment in bad condition, and respects their production deadlines. Usually, this complexity led plant managers to decide beforehand that it is not worth to implement a predictive maintenance program for legacy equipment, thus forfeiting the benefits of a modern maintenance approach. Many companies will keep on performing maintenance in their traditional way because they do not believe that a different approach can actually help them to save their money. The EU project programs proposes to change this mindset with its suite of modular solution that supports the plant managers through all their predictive maintenance journey by determining to which equipment it is profitable to deploy predictive maintenance, providing a maintenance platform that can be operated by engineers instead of data scientists, and integrating maintenance aspects with the production plans and with the factory everyday life. To set up a complete predictive maintenance program, the starting point is to compile a list of equipment maintained components and of their failure modes. Sometimes, predictive maintenance is the only strategy safe enough to apply, while in other cases, predictive maintenance might not be worth its investment, and different strategies may be taken into consideration. Program proposes a software-assisted FMECA module to chart all the failure causes, and a maintenance scheduler optimization module to identify the components for which a predictive maintenance approach is more profitable than the traditional corrective or preventive ones. The task of performing a FMECA is complex and time-consuming. Unless developed by a reliability expert team, FMECA worksheets are generally inconsistent and disorganized, and updating them can be even more complex. The program's FMECA improves existing applications since it supports the user through all the steps necessary to complete the analysis, provides an interactive tutorial for each phase that allows clear predefined options, exploit information collected and computed by the program suite to automatically fill the worksheets and to periodically reevaluate the risk of component failures, highlighting unreliable components, determines the components for which predictive maintenance is mandatory, and forwards relevant constraints to the allowed maintenance strategies. The MSO module aims to determine the most appropriate and cost-effective maintenance strategies and labor policies for all components of production equipment. The MSO integrates different software components. The live data analysis tool allows the automatic identification and characterization of reliability models for equipment components based on historical reports collected from the field. The R&M simulator evaluates the effects of different maintenance strategies on the reliability parameters by a Monte Carlo simulation algorithm. The LCC calculator considers all components of the cost function to provide figures on component, machine, and system level. To select the best maintenance strategies, a simulation-based genetic algorithm has been developed and implemented. The multi-objective optimization is driven by the minimization of the LCC and the maximization of availability, while considering the FUNMaker constraints. For each iteration, the reliability parameters are calculated by simulation, and, based on them, the LCC and availability are determined for the user-defined lifespan period. The genetic algorithm includes a clusterization extension which groups the maintenance of components to further reduce costs. Predictive maintenance is based on relevant factory data. This requires an IoT system that conditions, collects, cleans, synchronizes, and stores sensor data. Programs proposes its equipment control module. The data is then exploited by the different program solutions to determine the fitness for production of equipment components. The proposed solution has different degrees of confidence and speed, allowing to provide condition information from the very beginning of the program's platform deployment, and improving its robustness as more data becomes available. The program's equipment control module is a cyber-physical system comprised of the following components: a modular and insulated section of digital and analog inputs for connecting sensor wires, a programmable controller to process the inputs and relay data, an industrial PC acting as a gateway to the cloud database and performing real-time data acquisition from equipment controllers. Acquired data are uploaded to the program's database, making it available to all the program's modules for further analysis and exploitation. Data is also accessed directly at edge level to allow the adjustment of processing parameters to equipment condition, the execution of remote commands, and the tracking of the component's usage time. When the available amount of data is insufficient for more complex evaluation techniques, the quick rule estimates component rule by exploiting physics-based analytical model of mean time to failure, fed by monitored process signals and design data. The MTTF is calculated using the lifetime formulas given by the catalogs of the components manufacturers. Once the MTTF of a component is known, the rule can be ascertained as the difference between the MTTF and the usage time. So far, calculation algorithms have been implemented for machine tool ball screws, linear guideways, and spindle bearings. ASIA is a diagnostic module based on the system invariant analysis technology that uses a data-driven approach to evaluate the general status of equipment. ASIA allows the user to identify unexpected behavior of the equipment without any knowledge of the relevant models. At the beginning, when the dataset and training of algorithms is limited, the module only provides the expected state of the equipment. As the training time and ingested data increase, the diagnosis becomes more and more robust, and the ASIA output includes the prediction of the rule or concerned critical components of the equipment. To determine the rule of critical equipment components, a digital twin is a proper approach. Relevant physical models can be created by a three-stages methodology: definition and creation of components models, modeling of virtual sensors, tuning of the digital model parameters by fitting the simulated and measured singular responses. Once equipment components digital twin is available, it can be used to estimate the rule by predicting when the deviation of selected parameter exceeds a predefined threshold. In programs, this methodology has been applied to 6 degrees of freedom robot reducers and milling machine tool ball screws. Total productive maintenance is a production management methodology aiming at a continuous improvement of equipment effectiveness. Planned maintenance pillar requires to schedule maintenance tasks based on predicted failure times or on measured failure rates. The smart scheduling tool achieves this objective by merging programs platform information with factory legacy ERP system data, thus closing the whole production lifecycle. Training and education, focused improvement, and early equipment management TPM pillars requirement are granted by integrating maintenance information in everyday factory life by establishing a continuous communication between production and maintenance employees, thanks to the maintenance service platform. DSST feeds on data produced by other programs module to determine a weekly or monthly based schedule for maintenance activities, and then uses a heuristic algorithm to achieve the best integration between the computed maintenance schedule and the production activities programmed for the same period. The algorithm discretizes time into decision point, and at each one, alternatives are evaluated based on varying criteria, such as time and cost. The algorithm chooses the alternative with the best utility value and continues to the next decision point until an integrated schedule is determined. The program's MSP allows to notify interested personnel about the status of production equipment and planned activities by adopting a social network paradigm. In this way, people on the factory level can make informed decisions and best act when a problem arises. By using the MSP, operators may follow and participate in the factory maintenance management, monitor all collected parameters of a specified machine in the factory, remotely manage the production process, check for alarm condition and identify emerging problems, view real-time and archived data, and share the knowledge gathered from their maintenance experience. This picture gives an idea of the program's platform architecture. It is clear that the program's modules are connected into a single platform, and the architecture proves that no module is an island. Each one retrieves data from and provides results back to the platform. Modules implement service entry point based on REST technology to share information with the other ones. Program's platform will be tested on pilot lines from very different production context end users that currently follow the baseline of preventive maintenance. End users expect reduced breakdowns, downtimes, and overall maintenance costs. Easy maintenance management is possible even by untrained personnel. Improved quality by remote equipment monitoring and control. Auranac manufactures molds and tooling for the mass production casting industry by milling machine tools. Its major customers belong to the automotive sector. Calpac covers all part of solar thermal energy system production by its 6 degrees of freedom robots. Its selling points are both the residential market and industrial one. This is the current status of the project. DCM has been deployed on both the end user lines and currently allows to remotely monitor the selected equipment. Pilot lines have been enhanced with accelerometers, thermometers, and a vision system capable of verifying the quality of the welding process. Legacy maintenance information has been provided by the equipment producers to allow proper evaluation of the equipment components lifecycle data and make analysis. Production plans and equipment-specific information has been shared by the end user to allow modeling activities at all platform levels. All programs modules have been completed and deployed on dedicated cloud virtual machines. However, COVID-19 related issues delayed the performance of validation activities that will start only in September 2020. The whole project had to be extended by 6 months to end in March 2021. The program's platform comprises and interconnects all the modules described so far. Some of them are brand new in their concept, others improve existing solutions to allow an integrated management of the whole factory maintenance activities. Programs aid at demonstrating that the integration of different modules allows to exploit predictive maintenance further than usually achieved. A careful selection of maintenance strategies, including but not limited to predictive maintenance, allow to lower the life cycle cost of equipment while its availability increases. The predictive maintenance strategy can be profitably applied even to legacy equipment components. A predictive maintenance platform can be managed even by people with limited training if available data is properly exploited and decision-making support is provided. Thanks to these results, programs aim at getting plant managers to change long-held maintenance practices and finally introduce predictive maintenance in their production lines. Please note that details about the maintenance schedule optimization, the behavior prediction tool, and the maintenance service platform modules will be provided in the next presentation. Thanks for your attention.